everyone. Welcome to UAA Professional Development Seminar Series. Our presentation today is on Anchorage storm drain pipes, inspection results and findings. And our presenter is Matt
Steffel.
He's a PE. So I let you introduce yourself.
All right, thank you.
Thanks.
All right, welcome everybody to today's presentation. The topic is Anchorage storm drain pipes, inspection results and findings. My name is Matt Steffel. I own an engineering company here in town. We specialize in condition assessment. We inspect pipes, underground pipes. We also specialize in repairing those pipes with trenchless technology. So the talk today is really a big part of the business that we're involved in here in Anchorage. See if I can get this thing to work. Here we go. Okay, thank you. All right, we'll keep moving here. A little background about what the topic for today is. Anchorage is right now forming a stormwater utility. It's going to encompass all the stormwater pipes in the greater Anchorage area. The majority of the pipes are owned by the city of Anchorage, roughly about 80%. The remaining portion of the system is owned by the DOT, and there's some other private systems as well. One of the real driving factors here is that there are well-known serious problems with the corrugated metal pipe in the existing system. And that's really what the talk today is about. As you well know, that this issue is getting a lot of press lately. There was a newspaper article just this week on Wednesday on the front page was about fixing the aging drain pipes, and the city pursues a new stormwater utility. There have been a number of topics in front of the Anchorage Assembly about this issue. Some ordinances have been passed. They're moving forward, and they've also had some engineers and consultants involved in developing documents for them, which I'll talk about today. And that's the wrong way. There we go. So what does a stormwater utility do? The primary purpose is to keep the storm drain system operational, make sure it functions correctly, maintains it, cleans it, etc. And the purpose is to minimize problems in the city. Sinkholes, flooding. The picture on the right is a photograph of a flood caused by Chester Creek in the area of Arctic Boulevard and 19th Avenue. Defective storm drains can cause property damage. Emergency repairs. It's interesting that I'm here in the UAA building today, and there's an emergency repair happening right next door on 36th Avenue to repair a culvert that carries Chester Creek, and they had that road shut down for a couple of months this fall. So that's one of the things that a stormwater utility would try to prevent, or things like that are emergency repairs. A stormwater utility is also going to have a lot of good information about their system, mapping. They're going to understand what kind of condition their system is in, the location of where the problems are. And in our case here, the new utility, if it does form and eventually form, would maintain both pipes that are owned both by the City of Anchorage and also the Department of Transportation. So there was a study that was completed by the city. It was finished in January of this year. I'm going to talk a little bit about that. Basically, it's a guide for starting the new proposed stormwater utility in town. And this thing was completed by a number of qualified consultants here in Anchorage, some qualified engineers. It's a pretty good study. And they made some statements that I'm going to visit here. They identified that there's lack of good data about the existing system. And we know that from our personal experience working on it. They determined that the storm system in Anchorage is about 525 miles long. That's the pipe portion of it. That doesn't include the open channels and the streams, etc. Their report did not include any field inspection work, which is what I'm going to talk about today. But what they did do was they did a desktop analysis of the condition of the existing system, and That work was finished in the late in 2017, so it's about 2 years old right now. But it was a desktop analysis. I really didn't do any field work. They interviewed engineers who work with the city. They interviewed O&M staff and talked to both state and City of Anchorage engineers. In that report, they estimated that about 70% of the system here in Anchorage is corrugated metal pipe. That's about 380 miles of corrugated metal pipe. They also made the statement that all that CMP pipe is at or near failure today. Then there was a statement early in this study that that MOA staff had predicted that it could cost up to $1 billion to bring this existing storm system here up to standards. That's a big number for a community like ours. So today, what I'm going to talk about is I'm going to talk about CMP pipe and its failure mechanism. I'm going to talk about the condition of the Anchorage system based on some work that we've done recently, our firm, and then I'm also going to evaluate the results of the field data and give you a little bit more information about what the findings were from the work that we did. And here's a picture right here, a classic CMP failure. This is a CMP pipe located down at the Port of Anchorage. The sidewall is missing, got soil coming into the pipe. This happens to be a piece of CMP pipe that gets submerged in tidewater twice a day. So very, very susceptible to attack by corrosion. So let me tell you a little bit about what CMP pipe is made out of and what it is. These are pictures of good CMP pipes. So you're going to see a lot of photos today of pictures of bad CMP pipes. So for those of you that aren't familiar with CMP pipe, I see a lot of students in the room here today. It's a pipe made out of metal. It has it's thin metal. It's 1/16 to 3/16 of an inch wall thickness roughly. It's coated with a galvanized zinc coating. In Anchorage, predominantly most of the pipe is galvanized steel pipe. There is some aluminum pipe in Anchorage, but the majority of it is galvanized steel. There's a lot of different variations of corrugated metal pipe. Some of it's riveted. We've seen a lot of older ones that were built were riveted together. There's tar coatings. You can see pipe with tar coatings. Some of the CMP pipe available today has a polymer coating on it. So there's a lot of variations in this, but basically it's a pipe that uses the corrugations to make it strong and also reduce the thickness of the metal. So joints in the CMP pipe are typically bolted together with a coupling. Here's a photo here of a coupling. It's a bolt just like a compression coupling. Most CMP pipe at the coupling has some sort of a rubber gasket. They're not completely watertight. For the most part, they leak. We see a lot of CMP pipe that was assembled without even having a rubber gasket in it. One thing about CMP pipe to remember that it's considered a flexible pipe, similar like plastic or HDPE. It relies on the surrounding soil to support the pipe itself. That's not so critical in the smaller diameters, but it is critical in the larger diameters where you need a strong soil around the pipe to keep it from collapsing or deforming or collapsing from the top down. So the failing of CMP pipe is a serious problem in the Anchorage storm system. And a little bit more about corrugated metal pipe. It was patented in the 1890s, which was a surprise to me. I didn't realize that it had been designed that long ago. It really came into use in America in the 50s when President Eisenhower provided funding for these federal highway projects to build an interstate system across America, which was really about being able to transfer the military from one part of the country to the next. So they had all these federal highway projects. CMP pipe became very, very popular at that time. And the reason is because it was a lower cost pipe. And why is it lower cost? It's because it has less metal in it. The corrugations make it strong, but which results in being able to use a thinner metal. And you saw in the previous slide, that metal is 1/16 of an inch, an eighth of an inch, or 3/16 of an inch in thickness. So it's really pretty thin. In our community, the Municipality of Anchorage CMP pipe is roughly between 30 to 60 years old. And the city of Anchorage converted to plastic, or began converting to plastic around 1990, and which explains why most of the pipe in town is not any younger than about 30 years old. For the state of Alaska, their corrugated metal pipe ranges in age probably from about 15 to 50 years. They have not been as proactive as the city in terms of changing from corrugated metal to plastic, but we're beginning to see where the states obviously they understand that they have a problem with their system in regard to the CMP failing, and they're slowly starting to convert to plastic pipe. Their standard specifications still include corrugated metal. Here's a picture here of another defect in CMP. It's a pipe hole. You can see soil falling in to the pipe. So I'm going to talk about the mechanism with which corrugated metal pipe fails. And the primary mechanism is corrosion. On the both on the inside and the outside of the pipe. And water, if you have an aggressive water environment with a pH that's under 5 or over 8.5, that can aggressively attack CMP pipe. You can, which is one reason why we have that, that kind of a problem here in Anchorage. We have a lot of swampy areas. Organic activity in swampy areas can enhance corrosion. And the result is, you can see in the picture, eventually the corrosion attacks the metal and the metal just disappears. This photo here on this screen, it's a little bit hard to see, but it shows the metal that's missing on a corrugated piece of pipe that's got water basically about halfway up its depth, up to the spring line, and the bottom half of the pipe is very likely missing most of the metal. The damage occurs where, or is more serious, or occurs faster where there is continuous water or standing water or flowing water. Anchorage has a lot of high groundwater tables. We also have a lot of areas where, we know from our own personal experience, that quite a few of the pipes here in town are underwater, or the lower portion of them is underwater quite a bit. Or some of them obviously flow, or honestly flow continuously all the time. They're carrying some sort of groundwater from upstream or a portion of a river or creek. Another mechanism of failure in corrugated metal pipe is abrasion. And that's basically the wearing away of the inside surface from action caused by debris and sediment running down the pipe. And now CMP is more susceptible to abrasion than smooth pipes, and one of the reasons is because it's got these corrugations in it which create turbulence. And so the water's bouncing along, it's got some debris in it, some rocks or sand or whatever it might be, and they're striking the face of the corrugations as they rattle on down the pipe. And eventually that material wears away the coating, the thin zinc galvanized coating on the corrugated metal pipe, then exposes the metal underneath it, which may then be attacked by aggressive water or something else. So consequently, when the pipe is in an area where you have flow and an abrasive action, it's going to be more susceptible to failing sooner. And this picture here that you see on this slide shows some holes that have developed at the top of the corrugations. And that makes sense. The upstream side of the face of the corrugations, at the crown of the corrugation is where you're going to see most of your abrasive activity, and that's the first place where you're going to begin to see corrosion attack the metal and eventually eat the metal away so you have nothing left. We see a lot of pipes there where in this town here where the upper part of the corrugation, the crown part of the corrugation is gone, and the bottom part's still in place. So that's a little bit about abrasion in corrugated metal pipe. One of the most common places that you see the failure in the CMP is in the invert, which makes sense because that's where you have the water at, that's where you have the abrasion activity occurring. And at Anchorage, the majority of the culvert failures happen in the invert area. And usually that portion of the pipe's underwater, probably being some sort of something that's in the liquid itself. We do find cases where the corrugated metal pipe is corroded all the way around in a 360-degree circle. You know, you'll expose a piece of pipe or you'll look at it with a video camera and it's got holes all the way around it. And in a lot of cases, that's the aluminum pipe. My understanding is the aluminum doesn't have any kind of a protective coating, and that pipe has been installed in some sort of an environment that's causing it to corrode in 360-degree area around the whole entire pipe. But for the most part, those are few and far between. I mean, they do exist, but the majority of the problems that we have in our community here are in the invert of the CMP itself. Once the invert goes away, or is eaten away or disappears like in the picture here, then you have water flowing on top of the soil below the pipe. It starts to erode the soil out from around the pipe, which leads to this soil that's supposed to keep the pipe in place disappearing. And that eventually leads to an overall structural failure of the system itself. Buckling is a common failure mode that you see when the invert's missing on on a storm drain system. It's got some kind of loading above it from a road or something else that's heavy, and the pipe is beginning to collapse in on itself. It takes less corrosion to result in a failure of CMP pipe than a thicker circular metal pipe of the same strength. And let's just say, for example, I'm just comparing a Schedule 40 pipe as compared to a piece of CMP of the same size. You know, a Schedule 40 pipe might have a wall thickness that's 1/2 of an inch. You have a lot more metal there that can withstand corrosion over time. You also don't have the abrasion factor that happens because the invert or the inside of that pipe is smooth. You don't have this turbulence occurring. So the short answer is that if you had a round steel pipe with thicker metal, it's going to last longer than CMP in the same conditions. But of course, it's going to be more expensive too because it has more metal in it. So I'd like to talk a little bit about the projects that today that we accumulated and we're going to present. These are projects that we worked on, that our firm did starting in about 2007. There are other projects that have occurred around town by other people in the cities and the state and also private consultants. But we took all of our jobs and I've combined them into one database and looked at the information as a combined set. The total footage of our projects is about 160,000 feet. There are 19 different projects over about 30 sites spread out throughout town. And they varied in size, anywhere from 1,000 feet to, we had one project with the state that was 64,000 feet long that was just completed this year. So that's the field data that I'm going to talk about today. And this picture here is another pipe that's got a problem occurring. It's oval. It's probably a little difficult to see in this picture, but the crown is beginning to settle a little bit, and the shape it's becoming distorted. When we inspect these pipes, we use closed circuit television cameras, which is the photo on the left down there. That's a typical storm pipe inspection camera. It's got big tires on it so it can maneuver through debris, which is pretty common in storm drain lines. We utilize a downhole zoom camera, which is the photo on the upper right. That's a pretty neat little tool. It's got a real strong beam on it. A person can look at a storm pipe from the surface, and it'll zoom up a pipe up to like 300 feet if you have a pretty good reflection inside of the pipe you're looking at. It has the ability to record video as well as still photos. And you can get a lot done in quickly because you're not having to mobilize the camera and run it up and down the line. So the limitation, of course, with the zoom cameras, you can only see so far, and you can't look at defects real close. But anyways, it's one of the tools that we use. Some of the larger pipes are inspected with man entry methods. And then one of the things that we do too is we probe the inverts of the CMP with a hammer or a bar or a spud wrench or something to check the metal to see if it's soft or if there's no metal at all. And oftentimes the invert's under some debris or it's covered by water. You don't get a good look at it with the camera. So we use probing to check the integrity of the invert. And that's a technique that's been around for quite a while, actually, in regard to CMP inspections. So a little bit more about CMP inspections. They're a little bit different than your normal sanitary sewer pipe or other type of line. And it's important to have adequate lighting. A lot of storm drain lines are big, 36, 48. This image here is probably, I'm going to guess it's a 48-inch pipe. It's good to have good lighting so that you can see the entire pipe from the camera itself. We pay close attention when we're doing these inspections to look at the flow area because, as I explained earlier, for the most part, if you're going to have a problem in your pipe, it's probably going to be happening down near the bottom of it. Camera speed is, it's important to maintain the proper speed. If you go too fast down a corrugated pipe with the camera bounces up and down. So we try to be careful, it distorts the image. So you want to be cautious about going too fast. A lot of storm drains have debris in them, a lot of water. They need some sort of preparatory cleaning, which makes the work expensive. We were involved in a lot of projects where there's just not enough money to clean everything and look at it 100%. So most of the people that we work with want to utilize or spend their funding on the camera image, not so much the cleaning portion of it. So there are some cases where you can't inspect a pipe because it's got too much debris and other things in it that won't allow the camera to pass. Those cameras with the tires can only go through so much stuff. They're not, they can't motor through everything that's in these lines. When you're looking at a corrugated metal pipe with a camera visually, the defects are not always very apparent. It's difficult to see them in some cases. It's challenging to determine how much wall thickness you have left, especially when you're looking at a piece of metal that's 1/8 of an inch or 3/16 of an inch thick. You're looking at it with a camera, and it's pretty hard to figure out if you're missing a 1/16 inch of metal or not. So that's one of the challenges with inspecting CMP, which is why we try to follow up with some probing activity to confirm whether or not the invert's soft. And so, as I said earlier, surface corrosion versus significant metal loss is hard to identify. What's easy to identify in a lot of cases are holes, and that's really what you're looking for when you're doing a visual inspection of pipe like this. One of the things that we see sometimes is that there's a tendency to overestimate poor pipe condition. You'll see a lot of corrugated metal pipe that has some surface corrosion on it, and it looks like the pipe is rusting away. And you may find through probing that the metal itself is still relatively sound. So we caution people on being careful about overestimating what kind of condition their pipe might really be in. So now I'm going to talk about the field data that we acquired over the course of the last 12 years. This map shows the locations, and the red areas are the areas where the, I'm sorry. Okay. The red areas are the areas where the projects occurred, and in our projects about 127,000 feet of it was for the state, and 32,000 feet of it was for the city of Anchorage. And that's in comparison to the storm drain system, which contains, 80% city pipes and something less than 20% of state pipes. So the majority of our information is based on DOT pipe inspection work, but one of the large DOT projects was the one in the fourth bullet here, which was the 63,900 foot Department of DOT NHS project, we called it, National Highway System Project, which included 10 streets that were located around Anchorage. And there they are, A Street, Old Seward, International, Diamond, DeBar, Muldoon, Ingra. They were pretty much spread across the Anchorage Bowl area. And the thing that I want to point out here is that even though these were owned by the state, they're not owned by the city, but they're located in the city, and they're surrounded by pipes that are owned by the city of Anchorage. So for the most part, you're going to hear me recommend that this project that was done for the state really also represents some of the conditions that you might see in the city of Anchorage pipes in those areas. The other thing I'd like to point out on the map here is that you see this large red dot over by the airport. And this is some inspection work that we did for the airport in the ramp area out where the jets are coming and going from the terminal. And there's some interesting results that came out of that analysis, which I'll talk about later. But quite a bit of what I'm getting at here is that quite a bit of the work that we did for the state also involved looking at pipes in the airport area and were not parts of the street system in Anchorage. So here's a table that's a summary of the different projects that we worked on and the data that we got from them. And hopefully you can see that. It's a table with a lot of information on it. I'll go through and point out some of the important details in the next few slides. But when you look at this table, you can see that it's been broken into city-owned pipes and state-owned pipes. And the left-hand column is the project name. The numbers next to those project names kind of signify what year they were done in, 08, 2012, et cetera. You've got a column that tells you how many feet of pipe we inspected on each project. The number of segments, that's the third column. And when you look at these jobs, you're always trying to figure out, well, how many different segments you have. A segment basically is one pipe from end to end, one manhole to one manhole, or a culvert opening to a manhole, something like that. There's some other data here we'll talk about on the next few slides. Some comments about the overall condition, and then finally on the right-hand side, a note about whether or not we probed the inverts on the project. So first thing I'd like to point out about the information that we accumulated here is we found a lot of corrosion, and that's what these red circles are showing you, that that on 1, 2, 3, 4, 5, 6, 7, 8 projects out of 19, roughly half of them, we identified corrosion within the pipes. One of them down at the bottom, the third one up from the bottom, is surface corrosion. That was identified on a project that was performed at the airport. But all the rest of these are corrosion that's in the invert that is serious enough that there's some metal loss involved, and the pipes are in pretty poor shape. So those corrosion notes are also related to the invert probing, which are the two columns on the far right. And down near the bottom of the table, you can see where we probed inverts, and there was no metal loss. In some cases we found metal loss, in some cases we didn't. But that again just reiterates that in our community that corrosion is a big problem with the CMP pipe, and it's noted here on a number of different sites that we investigated. So let's talk a little bit about some of the significant defect data. which is outlined in this red box here on the table. And the one thing that we did is we determined how much each project, how much CMP was in each project, and what the percentage of pipe in that project was the CMP. And that's what the first two columns represent. You've got basically, like on the city of Anchorage pipes, which were a total of 32,000 feet, roughly 20,000 feet of that was corrugated metal pipe, or about 62%. So that basically compares favorably with what the study said, the recent study said, that 70% of the pipe in Anchorage is corrugated metal pipe. On the Department of Transportation projects, which is in the lower half of the table, the CMP portion was 77%. So both of these are within the 70% realm that came out of the findings, the desktop analysis. It was done and completed in the recent storm drain report. And then finally, the third column over here in this red box tells you what percentage or what portion of that CMP was considered defective. And it varies from a little bit to a lot. And there's some of the CMP only, like on the upper part of it on a project on 64th Avenue, only 13% of it was found to be defective. Then you see here in some cases 100% of the CMP was found to be defective. And these projects, we're called out to do these projects. It wasn't because they had a problem. Oftentimes it was related to a road improvement job. They wanted to make sure if they were going to fix the road, that they knew what kind of shape the pipes were in, and so they could fix them at the same time. In most cases, honestly, that's why we were called out to inspect the pipes and determine what kind of shape they're in. So a little bit about some of the data that came together when we looked at all these jobs combined. Another interesting characteristic that's within the red circle here is about the storm drain pipes that we looked at on the airport ramp area. For the most part, this is 30, 50, 60,000 feet of pipe. And for the most part, we didn't find any kind of invert corrosion at the airport. And we found some minor surface corrosion on the one project at the very bottom there, but we didn't find any, missing inverts, holes, corrosion holes over, quite a bit of volume of pipes. And the pipe age here is like they were put in about late 70s, early 80s. So they're not new pipes. They're 40 to 50 years old. And so this, is kind of an interesting example of a place where corrugated metal pipe has managed to survive longer than other parts of town. And if you look at, you ask a question, well, why is that? And the reason is, or what we think anyways, is that the airport ramp is pretty flat. It is flat. And the storm drain lines at the airport are on real flat slopes, on minimum grades. They're trying to prevent them from getting too deep, which means that the velocity in the pipes is relatively low, the flow velocity. And the other factor that comes into play is that they don't put a lot of sand on that ramp. So these storm drains at the ramp out of the airport are not carrying a lot of sediment. So, which means that there's a high probability that they're not being exposed to this abrasion problem that may occur in other parts of town where you have debris going down the pipe due to either high flow or something coming in from the catch basins. So, those are some of the factors that may explain why pipe has managed to survive out here longer than other parts of town. The other thing that comes into play here too is that the soils out at the airport are pretty consistent. They're fine grained. You have you get some areas where you get a little bit of peat, but it's possible, we've never measured it, but it's possible that the water at the airport is not as aggressive as other parts of Anchorage where you're located in a swamp, for example. So, if you're talking about corrugated metal pipe in our community and you look at the airport, you can say, well, that's a place where it seems to have survived fairly well. Just one of the things that sort of fell out of evaluating the data here from this little analysis. So I'm going to talk a little bit about the results from the Department of Transportation National Highway System storm pipe inspection work that we did. This is the project where that involved almost 64,000 feet of pipe. It was completed over the course of 2.5 years. And as I said earlier, this is a good representative of the conditions of the pipe in Anchorage. It's a pretty comprehensive report compared to some of the other work that we did. Some of the other investigations that we did were just mostly, hey, we want you to inspect the pipe and tell us what kind of shape it's in, and that's it, right? Tell us what condition it's in. We'll figure out what to do with it from then on. But on this project that we did for the Department of Transportation, they asked us to not only inspect the pipe, they wanted us to give them a summary or they wanted us to tell them what kind of condition it was in, and then they wanted us to make a recommendation on how to repair it, and also provide them a cost estimate or an estimated cost, an estimate of what those costs would be if they went out and did the repairs. So it was a little bit more comprehensive than some of the other projects that you saw on the previous list. And as I said earlier, there was about 10 sites located all over town. So a little bit of information from this project. So 27% of the pipe segments, or 27,000 feet, was identified as needing repairs now. So those are defects that when we looked at them, we said, if this utility owner is going to want to repair these things soon. There was obvious defects, holes, soil coming in through pore joints, things like that. So when I talk about how much the dollar cost came out to, it was an estimate based on fixing the pipe either now or in the near future. When we saw on this project, things that were catastrophically bad, they fixed them immediately, i.e., a collapsed pipe of soil coming in that was in a busy street that could eventually turn into a sinkhole. So on this job, 95% of the pipes were corrugated metal. So we had an opportunity to look at a lot of these kind of pipes, and about 40% of them were recommended for repair. And we went back and looked at some of the record drawings to figure out what the average age might be, and it was about 32 years. It seemed like a lot of these things were installed in the 70s and 80s when Anchorage grew and the streets were being upgraded, et cetera. So for the most part, the pipes that we looked at were not newer CMP installations. So this is a little bit of data about the costs that were generated from this project. We estimated that it would cost $7.9 million to repair the 27,000 feet of pipe that were identified for needing repairs. These costs are based on actual bid numbers that we have accumulated over the years for, there was like a handful of different types of repairs. And so we had unit costs for different types of repairs. We applied them to the pipe defects and eventually came up with this total construction cost of $7.9 million. And you can, for the 27,000 feet of pipe that we identified as having defects. So if you just take this number and begin to extrapolate it out, which we didn't do that in this study, but that's what I'll talk about here. If you added, let's just say, for example, 35% for engineering administration, maybe some pre-CCTV investigation work, your repair cost starts to jump up to roughly $10.7 million. And then if you took that $10.7 million and said, okay, well, what's this turn into in a price per foot basis to repair the 27,000 feet of pipe, it works out to be about $400 a foot. And so, which turns into a big number when you start dialing up the footage that you're going to fix. This picture on the right here is, pardon me?
What diameter are you using for form? What's the foot?
It varied because we had, on the diameters, we had a price per inch diameter on the different sizes. So we changed the per footage price based on pipe size, okay? The question was, what diameter pipe did we use in our estimate? And the answer is that the per footage price for the lining, for the pipe repair work varied with diameter size. So,
And Matt, did that include any of the structures, manholes, catch basins?
the question was, that include structures and manholes, and the answer is yes. Yeah, yeah, and I didn't talk about that here today, but yeah, but for the most part, storm drain manholes don't seem to have a lot of serious problems. But yes, we did have costs in there for manhole repair. Yeah.
Is space close enough that you can do CIPP?
Pardon me?
Are the manholes and access points spaced close enough, or did you have to add more access points?
Yeah, the question was, are the access points close enough to do the work? And the answer is yes. And when we estimated the 7.9 million, we added in some factors for traffic control at sites where, you know, they were on busy streets like International Airport Road or Minnesota, which for the most part, a lot of the DOT roads were on busy streets. We added a traffic control number to it. Yeah, yeah. Yes, sir?
Does that also include like solving any capacity issues? I know there's a lot of capacity issues around town, so is that just matching existing sizes?
Yeah, the question was, did that involve capacity analysis? And the answer is no. No, we didn't go that far into it. But in those construction costs, there were some pipes that needed to be dug up. There was excavation numbers in there. So the 5 categories were point repairs, either by trenchless methods or digging, CIPP lining, which is a very, very common way of fixing a storm drain pipe, open excavation repair. Those were the basic, the 5 or 6 basic repair methods that were used in our recommendations for how to repair each one of these storm drains. And so those were, unit costs were applied to those, and then that was extrapolated into a total number. And so the end result here was, you know, seat of the pants number of $400 a foot. So if we take that and kind of look ahead a little bit and look at the city's portion of the pipes, so the field data showed that 40% of the city of Anchorage CMP was found to have defects. And it was interesting that when you remember the chart from before, we had that upper part of it, which had all the city's pipes categorized. 40% of those CMP in those lines was defective. And in that single DOT project that included 64,000 feet of pipe, the result was the same. 40% of the CMP pipe in those DOT highway systems was slated to be repaired. And that just happened by accident. I didn't put that number up there to make it look good. So it was just that's the way it worked out. So I think that just a little piece of information that the city of Anchorage pipes are probably slightly older overall versus DOT pipes, which kind of makes sense because the city converted over to plastic in about 1990, but the DOT continued to install CMP. So overall, I think if there was some more work done here, you would probably find that the Anchorage pipes are slightly older than the state lines. One thing that's important to note is that we didn't evaluate life expectancy in this analysis, and that's always a question that you get when you're working with the utility. You know, how much longer is this pipe going to last? When do I need to think about fixing it? With corrugated metal, life expectancy is really challenging to predict because a lot of it already has some sort of surface corrosion on it, and you don't really, it's challenging to figure out, well, how long is that pipe going to last? How much is that corrosion eating into this thin metal? And so we didn't really get involved in any kind of analysis on that. When we're talking about defects here or making repairs, those are on things that are obvious problems with the pipe itself, holes, collapses, things that are obvious visual problems. And that's basically what the last bullet says. And it says, pipes with surface corrosion were visually not recommended for repair because it's challenging it's hard to tell an owner that this pipe needs to be fixed when it might just have some very thin surface corrosion on it, and it might still have 20 years of life left. So we didn't get involved in that kind of an analysis here when we looked at these repairs. Here's a photo here on the right that shows a corrugated metal pipe that the invert has very likely been eaten away on it. It's starting to collapse from the side, and the soil is starting to push the pipe in from the bottom. It's lost its structural strength. So if you take the information that we pulled together and you looked at how it might affect the city of Anchorage, so the study estimated that there was 380 miles of pipe. Actually, I'm talking about the storm system as a whole. You get a question from online? Okay. I'll answer this question when I get done here. So from earlier, we learned that there was roughly 380 miles of corrugated metal pipe in the Anchorage system. This is both state and city. And if you just took the assumption that 40% of that CMP needed to be repaired, use this $400 a foot number that we came up with from one of our projects, you're looking at a total value of $320 million to fix what may be defective today. And it's obvious, it's very likely that the number might be higher than 40%. When you talk with people that work on the systems all the time, they think that the portion of CMP that's defective is larger than 40%, and I can understand that. The study had a higher value. So then if you just took the 40% and bumped up to 60%, you're looking at an overall repair cost of roughly $500 million. So that's a big number, and but that's just when you took our field data, massage it a little bit, that's the kind of number that you come up with. So in conclusion, just a couple of more points here. Yes, improvements are being made here in Anchorage. As I talked about earlier, the city is implementing a much needed stormwater utility. The Department of Transportation is building a database. They're putting their video and pipe logs into a GIS system. That also will include other information that you would see, record drawing, et cetera. The project that we did for them was kind of the beginning of that, building that GIS system. And we've actually been involved in some projects since then where they're taking the information and starting to add it to it. The Department of Transportation recently purchased a TV camera so they can inspect the pipes themselves. And the city purchased a camera as well. I think it might have been their second version. And that was a little bit about what the article was in the paper on Wednesday mentioned. And looking at the pictures of the camera, they've got a storm drain camera that's looks pretty modern. So both of these owners are beginning to make some moves in terms of taking care of their storm drain pipes. Another bullet, CMP life expectancy can be longer in the right conditions, and I think what we see at the airport on the ramp is an example of that. There's probably some other parts of Anchorage where the conditions might be good for CMP. An example might be in the downtown area where you've got pretty good gravel, subsurface soils, low groundwater tables, corrugated metal pipes that are at pretty flat grades. We personally haven't done a lot of inspection work down there, but that might be a place where where you might see CMP last longer than other parts of town. And finally, so in the storm system here, these pipes are going to continue to deteriorate. The conditions are poor for them in a lot of places. This problem is going to get worse. And there's just no question that that this metal pipe in our system has a certain life expectancy, and then we're starting to reach it. So I'm going to answer any questions, and let me do this one that came online first. So the question is, does a CIP solution account for a change in conveyance? And I think I might have answered this once before. No, when you put a CIPP liner in, it basically has the same diameter as the hose pipe. And for corrugated metal pipe, you could probably expect a little bit better hydraulic capacity because the liner is smooth and it has a tendency to smooth out the corrugations. But for the most part, we always just often just say if you're going to put a liner inside of a corrugated metal pipe, you're probably, you might be stepping forward a little bit too much to assume that you're going to get a higher flow capacity out of that pipe. Any questions from the audience?
What's the life expectancy for CMP versus plastic pipe?
CMP versus plastic? The question is, what's the life expectancy for CMP versus plastic? I honestly don't know. I'll tell you what, I looked online today at a Contech website, which is a CMP supplier, and I saw numbers in there like, 30 to 50 years for CMP, right? But I can tell you from our own personal experience, we've looked at some plastic pipe in Anchorage, during our inspection work, and pipe that was installed quite a while ago, and it's really in very good condition compared to CMP pipe in that same project area. But I don't know the exact numbers. I think you could probably safely say that it's going to last longer here in town than metal. That answer your question, sir?
Yeah, I'm just kind of curious.
Okay. Yeah, I don't know what the.
Depends, but
Yeah. A little bit about pipe
advocating changing plastic, I'm just curious if what the sort of
life expectancy.
expectancy improvement is. Or we
Yeah.
end up with the same problem 50 years from now.
Yeah, I don't know the answer to that. I can tell you one thing though, that life expectancy predictions they're usually kind of a guess. Yeah. Yeah. James?
So I had a question because this is all about condition assessment. Utility, since I work for Able, we use the NASCO PACP system. Is there any talk about some sort of standard system for storm drain pipe in the industry to do condition assessments, or for either owner to adopt some sort of standard?
The question is there a national coding system similar to PAC that would be used in storm drains? Is that your question?
That's my question.
Yeah, and I don't know the answer to it, but I can tell you that I have not seen that yet. I would venture to say that you might be able to adapt the sanitary sewer PACP to storm drains. We have not done that yet. But I think what you're getting at is you would take that data and put it into a software program that would pop out a value for a defective number.
For prioritizing repair later on in the future, but I was just wondering if it's been started in the industry, because throughout the nation there's different utilities started for storm drain. I just wondered if it was following suit with the sewer that we're doing our work on.
Yeah, I have not seen any examples of where PACP has been adapted to storm systems yet. Yes, sir?
Am I correct in assuming that the deterioration of these storm drain pipes isn't a maintenance problem? Isn't a problem for lack of maintenance because it's all corrosion?
So the question is that the corrosion problem is due to a lack of maintenance?
No, it's not. It's not.
Oh, not due to a lack of maintenance.
Right.
Yeah, the corrosion, well, so the question is the corrosion problem that we're seeing in CMP due to lack of maintenance? And I think the answer there is that one thing is if there was proactive cleaning of the storm drains and removal of the sediment in the sumps, in the manholes, you would minimize the abrasion factor that's enhancing the corrosion in these CMP pipes, right? So if you minimize the amount of sediment that's going down the pipe, reduced it, I think that you would see an offset of reduced abrasion, which would therefore reduce corrosion.
Okay.
Yeah.
So the new stormwater utility, that would be their objective to do more maintenance?
Yes. The question is would that be one of the objectives of a new utility to do more maintenance? And I think the answer would be yes. Yeah. I mean, in today's world here, many of the storm drain projects, upgrade projects, are due to either an emergency happening or a road upgrade happening where they understand they want to fix the pipes underneath the road before they fix the road, or concurrently. Yeah. Yes, sir?
When you say plastic, what material is that?
What kind of plastic?
Yes.
The plastic pipe that we see most is called it's CPEP, which I think is corrugated polyethylene, which is it's got a smooth wall interior, but it's got corrugations on the outside that make it stronger, similar in the same manner that corrugated metal pipe is built. That's the pipe of choice in the storm drain systems here in town. Plastic pipe has got the same characteristics as metal CMP, in that the soil is a big factor in supporting the pipe. It's important that the pipe be bedded properly so it doesn't collapse over time. Yes, sir?
What kind of lifespan are you seeing for the cast in place versus a fresh install, considering I think cast in place is quite a bit thinner wall?
So how does the life expectancy of cured in place pipe compare to brand new pipe? So the industry, the cured in place pipe industry has made a statement for many, many years that their cured in place pipe liners have a 50-year life. And that product was invented in the 70s. So, right now we are at about the 50-year period. And I can tell you that it's probably got a life expectancy that's longer than 50 years. Yeah.
A lot of technology that they used up until about 10 years ago didn't actually hold pressure, didn't hold water. So.
Yeah. In cured in place pipe, a lot of the technologies until just recently weren't pressure.
Yeah, they would.
Yeah.
Even a couple inches of water, it would leak through. So it's really only the last 10 years that they've got the technology to the point that it's actually pressure bearing.
Yeah, the question was that CMP liners are somewhat permeable. I think the RD would agree they actually have a system in place now that's in use in Europe where they measure permeability. And so it's got some details on different liner manufacturers, liner types, and permeability values. So, got another question online. This is like a salesman when he gets on the phone and he doesn't serve the counter. Says, do you think that there would be an economy of scale that would make the repairs less expensive as the contractors doing the work found deficiencies? I want to say yes, but for the most part, our cost estimates are based on bid numbers on projects where you've got contractors doing a certain amount of volume here in Anchorage. You might gain a little bit from a scale of economy, but I don't think it would be a lot. And then the other question was, are the areas needing repair grouped together or spread out all over the city? The answer to that is that the areas needing repair, they're going to be grouped together, but they are also spread all over the city. So the answer is both. And that's really based on the conditions and the age of the pipe and the area that you're working in. But we haven't found a place in the city yet where everything in there is in 100% good shape. So I want to say that this problem with defective CMP is widespread across the entire bowl.
Was any of your inspection work on fin drain systems or just solid pipe?
The question was about whether we've inspected fin drains, and the answer is yes, we have. And I would venture to say the conditions are the same as what you're seeing from other CMP pipe. Yeah. Yes, sir?
Do you run any risk analysis or do you use any software to decide when is the right time to do the repair or when is the right time to do the replacement?
So the question is there software that would help us predict when to do the right time for the repair or the replacement? I don't personally know of any. You got to have good data to make that decision. And that's one of the things that a utility would do. They're going to have mapping data. They're going to know where their old pipes are at. They're going to begin to keep a repair record and probably lump their repairs into certain parts of town, and then they're going to begin to understand where their problems are. So they would be using computers in that, but I don't know of a software that they could just throw numbers into and pop out an answer.
Well, if there is no more
Okay.
question, join me thanking our presenters for a great presentation.
Thank you.